Welcome back. So our speaker this afternoon is Professor Andressa Cerqueira from the Federal University of São Carlos, and she'll be talking about estimating the number of communities of networks.
Good afternoon, everyone. So thank you, Roberto. I'm not going to thank the organizing committee for inviting me to be here, but I would like to thank you, Roberto, to give me the opportunity to give this talk in this week. So actually, it's always a pleasure to be here at IMPA. And this is because the first talk of my life I gave here at IMPA. So Roberto was there, and it was exactly in this corner. I was exactly in this corner. So for me, it's a pleasure to be here. It's part of my academic life. So today, I'm going to talk about the estimation of the number of communities and networks. So the last 2 weeks, we have heard a lot about inferential problems on networks. And for example, from Jesus' talk today, Jesus talking about, for example, community detection. And to do community detection, you need to first fix how many communities you have in the network, and then you estimate the communities. So I'm going to talk more about this problem of estimating the number of communities. But as a statistician, as Jesus said today, we need to establish what statistical model we are going to work on. So the statistical model that I'm going to work on, you know very well, so is the stochastic block model. So I will define again the stochastic block model just because here I'm using different notation, so just to make things clear. It's not that different, but still. So in this, I told you, in this model, we have we have a network with n vertices, and for each node of the network, we have a community assigned to that node. So here I'm saying that we have K0 communities. So K0 here will be like the true number of communities of the network. And the random variables, the communities are, for us, is ID random variables, such that the probability of node I belongs to community A is given by pi A. So here we have a vector of probabilities, so a vector of the K0 probabilities, and here I'm thinking about K0 is no, at least at this point. So we call these variables the latent variables of the model because we don't observe these variables. They are hidden. So this is the name that we give to these kind of variables. So the variables that we observe in this model is the edges of the graph. So for us, just the adjacent symmetrics of the graph. So the observed variables is the adjacent symmetrics of the graph, and then we define each entity of the graph. Given that I know that node I belongs to community A and node J belongs to community B, the existence of an edge between vertices A and G is distributed as a Bernoulli random variable in such a way that the probability, the parameter of the Bernoulli depends on the communities of the nodes. So for each pair of node, we have here a probability for this Bernoulli. So we can put all these probabilities in one matrix that I call P. So this is a symmetric matrix of size K0 by K0. So this is the matrix that I think that Jesus called like B, right? For me, it's P. And so this is the variables that we observe. So in this statistical model, we have the latent random variables, the observed random variables, and we also can define here the parametric space. So just to make things easier, I will define here a new parameter vector theta. That's just the vector of probabilities pi and the matrix with the probabilities associated with the Bernoulli P. And for each, if I fix the number of communities as K, for example, I have here that P is just a vector, a probability vector, and here I have all the possible symmetric matrix. So this is the parametric space. Okay. So this is the statistical model that I will work on. So we have talked a lot during these weeks about likelihood, the spectral methods, optimization, whatever. So it's time to say what is a likelihood, or write some explicitly the formula of the likelihood that we have talked a lot. So first, I will write what we call completely likelihood. So for the completely likelihood, I just see the joint distribution of the communities and the adjacency matrix. So here, I have this expression for the complete likelihood. That's just the first part comes from the fact that the variables z are independent, are actually IID. And here I have the probability of a node belongs to community A just to the power of how many nodes belongs to community A in this network. And the second part comes from the Bernoulli distribution, right? So here, I just fix a pair of communities, and then I have that the probability to have an edge between community A and B up to the power of how many edges I have between communities A and B. Okay, it's the same thing for how many zeros I observe. Okay, this is just the joint distribution, not that difficult. So in this talk, I'm going to work with this distribution here. So this is the complete likelihood. Okay. So now let's recall a little bit some inferential problems that we have when we are working with SBM. So suppose that I observe a network. So here I observe a graph, a network that comes from the SBM, where I have, let's say, that the true communities are Z0, and the true parameters that generated this model is θ0, P0, and P0. So the first problem is community detection, as Jesus explained to us today and Keith explained to us last week. So for community detection, what we want to do is estimate the communities. So I fix K. So I suppose that I know how many communities I have, and then I just estimate the communities. So here we have this process. So you give to me a network, right? The adjacency matrix of the network, and then the network. You can apply any method, so it can be based on likelihood, spectral, whatever. And then we just return as the output of this method the estimation of the communities. I think Jesus is going to talk more about this problem next week, right? The second problem is parameter estimation. So we have the parameters of the model, theta, and then I would like to estimate these parameters. So what we can do is, again, I'm going to suppose that the number of communities known. Since the number of communities known, I can do community detection, so I can estimate the communities. And then I will use the estimated community, so z hat, to estimate the parameters of the model. So what I should do, just come back to the log completely likelihood, to this expression that I have shown you before, this one. I just plug in here the z hat instead of z, and then just try to maximize this function, or maximize the log of this function. So if we do so, we need to find theta that maximizes the log completely likelihood. And what we got here is that p hat A, so the probability to have a node in community A is just how many nodes are in community A in z hat divided by the number of nodes in the graph. And the same for the p hat. So the probability to have an edge between nodes that belongs to community A and B is just how many edges I have in this using the z hat, right? So how many edges I have between communities A, B divided by how many pair of nodes I have between communities A and B. So this is the maximum likelihood estimator for these parameters. So if you know how to estimate well the communities, so if z hat is very close to the true one, you are going to have also a very good estimator for the parameters, right? And now, finally, The third problem, that should be actually the first one, right? But the third problem is how to estimate the number of communities. Because to do community detection, to estimate the parameters, I need to fix or I need to assume that I know how many communities are in my network. So this is a problem that we call like has model selection. And there are some different methods that try to estimate the number of communities. So we have methods based on the cross-validation that Jesus mentioned a little bit about cross-validation today. We have methods that's based on the spectrum of the graph. So we have also spectral methods. Methods based on the information theory, so minimum length description, and methods that are based on the likelihood. Right? So in this talk, I will focus only on methods that's based on the likelihood. So don't ask me about the others, right? So today I'm going just to focus on likelihood. So I'm going to talk a little bit about all these works here. Okay, but I have mentioned the complete likelihood. What is the likelihood of the model? So the likelihood of the model is just the sum over all possible communities of the complete likelihood, right? Of the joint distribution of my graph and the community. So this is the quantity that I'm going to work on. So what I need to do is just, I have this expression here. I add a sum over all possible z's, and I'm going to work with this quantity. Okay. But at this point, you can think, okay, I have learned about likelihood. So what we can do, for example, is to estimate the parameters. What we have done is just here, is to maximize the log complete likelihood. So one, guess should be, okay, I can think that k is a parameter, and then what I can do is just fix a number of community, and then calculate the maximum likelihood, take another number of community, calculate the maximum likelihood, and then I just pick the k that makes the likelihood as higher as possible, right? So, okay, what's the problem if I define this estimator? So when I define this estimator, you give me a network, and then I will give to you that k hat is equal to n. You give me another network, and then I give to you that k hat is equal to n. Okay? So why that thing happens, and then we don't have this problem when we are making inference about theta, for example? So here, when we change k, we change what we call the complexity of the model. Because when I change k, I change the parameter space where I'm looking for, right? And then when I change the parameter space, what happens with the likelihood is that the likelihood is an increasing function. I'm sorry because it's not possible to see, but here this x is just k, right? So this is k, the number of communities. And then I see that the log likelihood is an increasing function, right? So suppose that I have a network with 5 communities, right? So I just write this dot line. I have a network with 5 communities. So when I see this picture here, what I can realize is that, okay, the log likelihood, log maximum likelihood is an increasing function, but this function increases faster until the true number of communities, and after that, it's still increasing, but slower, right? So what we can try to do, okay, I would like, in some sense, try to penalize big values of k, right? I don't want to have a model that's very complex. I don't want to add a lot of parameters in my model. So what I can do is just add here a penalty term. When I add here a penalty term that is a function that increases with k and also with n, that's the size of the network, if I choose the penalty term in a very good way, I will see that that happens. So the k that's maximizing this new function is the correct k. So this gives us an intuition, okay, this is a good estimator. This is the estimation, this is the estimators that I'm going to looking for, right? Is that clear? Okay. So it's well known in statistics, Bayesian information criteria that we use in very different areas, for example, also for regression or other, if you're applying or fitting some data, we're using other methods. And the BIC criterion tell us that the penalty function should be in the form of 1.5 number of parameters of the model times the log of the sample size. Okay, so it would be like log of n squared for us, but still log n, right? So I'm going to come back to the BAC later. But let's just keep in mind that they use, in statistics, we use a lot of this criteria, right? Okay, so in 2017, Wang and Bickel proposed the first, not exactly the first method for estimating the number of communities, but the first one that they get some interesting results about the consistency of this method. So they propose this estimator that they use the maximum likelihood, and then they penalize it by this penalty function. So this penalty function is not exactly BAC, because here we have like k squared n log n. Right? It's much bigger than just log n. So for this estimator, they proved that this estimator is weakly consistent to estimate K0, to estimate the true number of communities. So what that means? That means that the probability of this estimator be equal to the true number of communities goes to 1, has n goes to infinity, has the size of the network increases, right? So I just forgot to say that lambda here is just some parameters. It does not depend on k or n, right? It's just a constant. Okay, so, wait, sorry, yes. Cross-validation. Yeah. They explain one method in the work, in the paper, that they do like cross-validation to estimate lambda. Mm-hmm.
Is this for the dense case?
I will tell more about the sparse case. Yeah, but this is for sparse in this case, but I will explain exactly what's the sparse case that they are going to look at. Thank you. All right. More questions? Okay, so what's the point here? If you guys remember Jesus' talk, suppose that you give me a network, and then what I can do, I can just compute this, and then I have a good estimation for the true number of communities. But the problem is, if you give me a network, it's very hard to compute the likelihood. Right? Jesus told us this today, that to compute the likelihood, I have here in the likelihood the sum over all possible communities. So this is intractable. So, okay, I have a really good estimator that I proved that works very well, but I can use, right? So what we should do? So here, you can try to use a method to approximate the likelihood, not use exactly the likelihood. But in this work, what they propose to do is just replace the maximum likelihood here by what we call the maximum profile likelihood. So what they do here, they just look at the complete likelihood. So the complete likelihood is that expression that I show you at the beginning of this presentation. And what they do is like, so this quantity now depends on the communities. So first, I fix K. First, I do community detection, have z hat, and then with the z hat, I estimate theta, and then it's done. I know how to compute this quantity, because I know how to compute the estimators for theta, given z, right? So, okay, it's better to use this quantity here, and in the same paper, they also proved that this estimator that you just replace the maximum likelihood by the maximum profile likelihood the estimator is still consistent, right? I mean, there are some conditions on the community detection. I mean, you need to use a method to estimate the communities that I think is not, I don't know if they really need to be like strongly consistent, but maybe you need to have like wiki recover or something like that, right? Okay. So
just one question. Can they prove that this works, or do they?
Yeah, they proved. Yeah, it works. Yeah. Okay. Yes, the same conditions that I showed. It's mysteries. It's just a mystery. Okay. Next, after this work in 2019, you and co-authors proposed what they called correct and Bayes information criterion. So it's correct BAC. Remember the BAC that I have told before. So what they did in this work, so now they look at this quantity because it's easier to compute. So, okay, I'm not going to look at the maximum likelihood anymore, just look at the maximum profile likelihood. And what's interesting here is that they have now this penalty term. So they changed the penalty term. So this penalty term is of order k squared log n, right? So plus a term that increases with n, right? So the previous one is n log n. And this one is n plus something that log n, so it's almost log n, almost n, right? And why they call this BAC? Because when I'm looking at this quantity here, if I use the BAC penalty that we use, it's just 1.5 number of parameters log n. In the case of the stochastic block model, will be k plus 1 divided by 2 log n, right? So we see this quantity here that appears here. So they call corrected because to prove that this is consistent, they need to add an extra term here, right? So this is why they called correct and Bayesian BAC. And what they prove that it's the same thing. They prove that this estimator is weakly consistent to estimate the true number of communities. Okay. So now, open problem, Roberto. So this is my open problem to you for the next weeks. So okay, you see, we can use like maximum likelihood, but I replace maximum likelihood by maximum profile likelihood. So it's possible to use another function that's based on the likelihood. I just plug in this function here, try to find the correct penalty, a good one, and then prove that this estimator is consistent. Is it possible? So this is the open problem. And you also need to have something that's very easy to implement and better than all the other methods in the literature. It's this kind of problems that we are interested in statistics, right? So what we did in 2020, we proposed use instead of likelihood or instead of the profile likelihood, the integrated likelihood. So it's a quantity based on the likelihood. So what is this quantity here? I just take the likelihood, so I can look at this quantity as, for example, probability to have a network given the parameters, right? So if I give here a distribution for the parameters, and I just integrate it out the parameters, I have the marginal distribution of the network, right? I'm just integrated the joint distribution. So this is why we call integrated likelihood. So we give a probability distribution for the parameters, and then we integrate it out the parameters. And then we define the penalized estimator, just like the other ones, but here I use the log of the integrated likelihood minus a penalty term. So I'm going to work with this estimator. Okay, so the point here, how do I choose the distribution theta, right? So I'm giving a distribution for the parameters of the model. We know that Bayesians do this a lot. So we are going to use some ideas for Bayesian inference. So what we do here is just try to give a prior distribution for p and pi that conjugates with the distributions that we have. So in other words, I just want to choose distributions that help me to make all the calculations that I need, right? But you just cut this part from the, from the video, otherwise the Bayesians will be very mad with me. So what distribution I choose? I choose so pi, as Jesus told today, is like a multinomial distribution. So I just give to pi a prior is a Dirichlet that conjugates with multinomial. So this is just a Dirichlet with parameters 1.5, 1.5, 1.5. We have here k parameters. And for each entry of the matrix P, I give a beta distribution with parameters 1.5, 1.5. Right? So ID. So the formula for this probability distribution for the parameters have this expression here. Right? So I just write here the likelihood, all that big formula, plug in this distribution, make all the computations, and then I have K, this distribution. Then I need to work with this quantity. But again, I'm using the likelihood, right? So I don't know how to compute the likelihood. So how I compute K, right? So in 2012, Latouche, Birmel, and Ambroise, they proposed what they call a variational Bayesian algorithm to approximate this integrated likelihood. Okay? So the idea is the same that as Jesus explained to us today. To approximate this quantity, I can use an IEM algorithm, but I cannot use an IEM algorithm because I cannot calculate some conditional distributions. So instead of using an IEM algorithm, I'm going to use a variational algorithm. But here, in this case, I have priors for the parameters. So instead of use a variational algorithm, I'm going to use a rational Bayesian algorithm, right? So in this work, they propose this algorithm, and they also propose this estimator here. So is integrated likelihood variational base. That's just the maximum of this quantity. So it's different from what I'm proposing because I have the penalty term, right? And for this, they just studied this through simulations. There is no results about this estimator. But I'm going to come back to this estimator later. Let's just move on for the estimator that we are proposing. So with the penalty term, it's possible to prove that if I choose an appropriate penalty term, I have that this estimator is equal to K0, the true number of communities somewhat surely, right? So here, the penalty term has this expression, but it's almost, let's say, K to the power 3 log n, right? If we just look at this expression here. Something like that, times a constant, right? So here it's what we call a strongly consistent estimator because we have a more short convergence instead of convergence in probability, right? This is the difference there from these works. And if we compare, I'm going to compare the penalty in the next slide because I think it's easier. So let's talk about sparsity, right? So what happens, actually, those results works well when you have a dense network, right? Everything works well when we have a dense network. So what happens when we have a sparse network? So let's consider this sparse regime where I just write the matrix P has a parameter rho n times another matrix S0. So rho n is the parameter that will control the sparsity of the model, and the matrix S here is fixed. It does not depend on n, right? And I want that rho n goes to 0. So if rho n goes to 0, my network is sparse. So let's compare all these estimators. So for the penalized maximum likelihood, they prove that if rho n goes to 0 at this height here, so n rho n divided by log n goes to infinity, they have the consistency of their estimator. The same thing holds if we are looking at the correct BAC estimator, right? And for the integrated likelihood estimator, we had something different, that rho n needs to go to 0 at the height and rho n goes to infinity. So what that rates show us? As Jesus told today at the end of his presentation, at this rate here, we can think that rho n should be greater than log n divided by n, right? So in this case, it's possible to, we have like exact recover, right? At this rate, we have exact recover for the communities. And for the rate for the integrated likelihood, rho n should be greater than 1 over n, that we just need to have what we call like weak recover, right? So for this method here, we can have a sparse network, right? So this is really nice. And another thing is that if we compare the penalty terms. So for the first one, the penalized maximum likelihood, the penalty term is like very huge because it's n log n, right? And we know for BAC that we should have something like log n, right? K squared log n. For the next one, this is log n. This is basically n, right? We have two terms here, n and log n. And for the integrated likelihood, we got something k to the power 3 log n. Almost the BAC penalty term. So this is interesting because we don't need to penalize too much, actually. And it's proven through empirical results, through simulations, that these estimators here should work well if we have a BAC penalty function. So something like k squared log n, right? It's possible to see this through simulations, but it's not done yet, right? So maybe you need to wait until the end of this year that hopefully we are going to put on archive on paper that we are able to prove a BAC penalty for the maximum likelihood. Let's see. There are some gaps, but hopefully we can fill. It's not an open problem, okay? Just to make it clear. Okay. Okay, all of these things we have for the SBM. But Keith told us last week that, okay, SBM is not interesting if you're going to analyze real networks, right? Because the expected degree is the same for all the nodes. So they propose what they call degree-corrected stochastic block models in such a way that they try to have different degrees for the nodes. So in this model, I mean, for the latent random variables is the same, right? But for the observed random variables, here I'm going to use the notation of the model that they proposed at the first time. That's from Carrier-Newman 2011. But I think that Keith showed a different model. It's just using a Bernoulli distribution. But I'm going to use the model that they proposed. So for the observed random variables, I need to look if node I belongs to community A, node J belongs to community B, then the weight, let's say like that, the weight of the connection between I and J is given by a Poisson with parameter that depends on the communities and also on what Keith called popularity of the nodes. So some parameters that here I'm using this W, right? So for identificability of this model, they need to suppose that if you sum these popularity parameters, this should be like I equals to A, right? So if I sum these popularity parameters in a community, this should give me the number of nodes that are in this community. So this is just for identificability of this model. So the parametric space, now we have one more parameter in the parametric space, that's this W's, right? Let me see if yes, they're correct here. Okay. So now P, I just use the same letter, but P here now is not, the entries are not in 0, 1. This is just the mean of the Poisson. Right? So when we look at this degree correct stochastic block model, we can also define the integrated likelihood, right? I can define the same way, but I need to change the the distribution for the parameters, because now I have actually any more parameters, right? The W's. So what we did in this case is give a Dirichlet to pi, same thing. But now, since we have a Poisson, I give a gamma distribution with these parameters for each entry of the matrix P in the independent way. And for the popularity parameters, we are going to give the Dirichlet distribution. Right? Okay, so again, I didn't write the expression for this distribution because it's a huge one, but we just plug in the distribution here, write the likelihood, and then compute this stuff, and then it's okay. We work with this quantity. So in 2024, what was proved is that if I look at this estimator here, so I just take the log of the integrated likelihood for the degree correct stochastic block model, and here I have a penalty term that the first part is exactly has this SBM, right? And the second part is n log n, right? So why now we have n log n? So recall that the BIC tells us that the penalty should be number of parameters log n. Now I have these popularity parameters. I have more n parameters. So now the number of parameters depends on n. This is why we got here, where? Here, this n, yeah. Was just thinking if it's n log n, but yeah. So this comes from the SBM, and then this part, this n here, comes because now I have more parameters that depends on n. So this estimator is equal to the true number of communities almost surely. Okay. For the sparsity, we also have some results. So, they, in the same papers, they also proved for the case for the degree corrected, right? So this is why I didn't show, but they have the proofs that the penalized maximum likelihood holds is consistent for the degree corrected, and the corrected BAC is also consistent. But for the penalized maximum likelihood, the height that they got is something like whole n should be greater than log n divided by square root of n. For the corrected BAC, they still have the same, right? But for the integrated likelihood, now we don't get like n whole n goes to infinity, so greater than 1 over n. Here we also had this sparsity term should be greater than log n divided by n. Right? So in the same regime, that's possible to have exact recover. Right? But again, here the penalty function is not that good because because of the W. So we got this extra term here, and for them it's the same penalty function. Right? Okay.
The BIC penalty would be what in this case? Sorry.
The BIC in this case, it will be n log n, k squared n log n.
K squared?
Yeah, because the number of parameters would be like k squared n. Yeah. Okay, let's see. I bring this simulation, but please don't look at the labels because it doesn't make any sense now because I changed everything here. But I can explain what that means. So here I'm considering a network that's not that big, so I have 500 nodes. Here, I'm considering what we call a balanced network. So the vector of probability pi is just 1 divided by the number of communities. I have 3 communities here. So I have the same number of nodes in each community. And in this setting here, we have what we call unbalanced communities, unbalanced network. So here I have 20% of nodes in community 1, 50% of the nodes in community 2, and 30% of nodes in community 3. So I have unbalanced communities. So I'm going to explain the labels. So here is the how many times the proportion of correct that my estimator estimate correctly the true number of communities. So estimate 3, right? And here I have rho n, so the sparsity parameter. So the blue line here represents the integrated likelihood estimator, right? The red line here represents the penalized maximum likelihood estimator. I don't have the correct BAC here because the time that I did this figure for the paper, they're not published yet, so this is why I don't have. Shame on me. The green one is a method based on the spectrum of the graph. This is the green one. And the purple one is the cross-validation method. This is the method based on cross-validation. So what we have here, so it's possible to see that the integrated likelihood estimator is better than the penalized maximum likelihood. Why? Because of the term, the penalty term. The penalty term that we use is like log n. If for the penalized likelihood is n log n, so you are penalizing too much. So then makes you not take the true number of communities when the network is sparse, right? But what's interesting here is that when we use, actually this is happens most of the time, that when we use likelihood, likelihood methods should work well when we have unbalanced communities, because through the likelihood it's possible in some way to detect this difference, because this is in the likelihood, this is written in the likelihood. So we can see here that the integrated likelihood method, okay, forget this part here, but is better than the other ones, right? I mean, because we can find this unbalanced structure in the network, right? And has this null, sometimes the spectral method, so where is the spectrum, is the green one. It's not that good when you have unbalanced communities. Maybe, I don't know if Jesus is going to talk more about this, but I really would like to hear some explanation why this happens, because I see a lot of this happen in practice when I try to use these spectrum algorithms for unbalanced networks. And finally, the final remark, the kind of the second open problem, right? So here, remember that I told you that to approximate the integrated likelihood, the authors propose also an estimator. And their estimator does not have the penalty term, right? So let's see what happens when we have the penalty term and then when we don't have the penalty term. So this is why I try to show here. So for this is unbalanced. Sorry, this is balanced. This table here is unbalanced. Rho n here is varying. So I have here the integrated likelihood with the penalty term and the integrated likelihood variational base without the penalty term. And this is the proportion of times that I correctly estimated the true number of communities. That's 3 in this case. So we can see that without the penalty term, it's less better, right? So actually, we don't need to penalize this estimator. So this is interesting. And why? Because when you write this quantity, let me take this expression here, and I integrate it out, I'm kind of making the penalizing thing here when I do this. So I don't need to penalize again, right? So this is a kind of open problem spoiler. This is a kind of open problem that I don't know how to resolve, right? I don't know how to prove. That's not necessary to have the penalty term here. But maybe when we have the consistency for the BAC, we are going to be able to prove that's not necessary to have the penalty term. So kind of open problem, all right? If you want to take a look on that. So this fact is very interesting. And actually, it's known, for example, if you are, I think, in the hidden Markov model, so when you are trying to estimate the number of hidden states in the hidden Markov model, and use an estimator like this, it's proved already that we don't need to penalize, right? So probably the same thing happens here because kind of similar, right? We have a hidden thing that's just the communities, and then we would like to estimate how many communities are there, just like estimating the number of the hidden states. So yeah, actually to prove all this stuff, we borrowed a lot of ideas from how they prove these results for the hidden Markov models. Okay. So that's all. Thanks for your attention.